Welcome to Course 4, Module 5, Chapter 14, Measuring and Managing the Transition to Circular Supply Chains. This presentation explains why changing supply chains from linear to circular models also requires changing the way performance is measured. Traditional accounting often rewards extraction, low purchase prices, and speed, while circular systems depend on recovery, reuse, resilience, and collaboration. Throughout the chapter, we will move from the limits of familiar metrics to practical tools for assessing material circularity, Scope 3 emissions, avoided emissions, and operational dashboards. The central message is that circular transition is not only a technical redesign of products or logistics. It is also a measurement transition, from narrow short-term efficiency toward regenerative performance across economic, environmental, and social dimensions. Today, we begin with a core problem. Traditional metrics create a blind spot because they were designed for linear supply chains. Then we examine two common examples, purchase price variance and lead time, and discuss why they are useful but incomplete. The middle sections introduce frameworks that help balance short-term efficiency with long-term resilience, including take-back systems, industrial symbiosis, and circular business model capabilities. We then move into measurement methods for material circularity, operational dashboards, Scope 3 carbon accounting, and avoided emissions from recycled materials. Finally, the chapter closes with global case studies and a conclusion that connects measurement, governance, digital transparency, and stakeholder coordination. This structure moves from problem diagnosis to practical managerial response. This section introduces a main challenge. Circular supply chains need different metrics than linear systems. To manage reuse, recovery, and regeneration, organizations must measure value beyond cost, speed, and throughput. The key point on this slide is that traditional indicators are not neutral. They guide behavior toward what they are designed to optimize. In a linear supply chain, metrics such as purchase cost, delivery speed, and short-term productivity can be very helpful. However, they were not built to recognize waste prevention, reverse logistics, remanufacturing, or long-term ecosystem value. As a result, circular initiatives may look unattractive because their benefits are delayed, shared across partners, or expressed in environmental and social terms. The chapter argues that this creates a circularity blind spot. Organizations may be improving real system performance, but if those improvements are invisible to the scorecard, decision makers can underestimate their strategic value. The first managerial task is making those hidden benefits visible. Circular supply chains require reverse logistics, because materials must flow back from users into recovery systems. They require resource recovery, because waste needs to become an input again. They also require stakeholder coordination, since suppliers, recyclers, customers, regulators, and communities often share responsibility for outcomes. In addition, circular performance includes regenerative value, social outcomes, and digital traceability. These are not easily captured by a simple cost or speed indicator. The implication is that benchmarking must expand. Managers need measures that show whether material loops are functioning, whether partners are coordinating effectively, and whether circular value is actually being created over time. Without these indicators, circular progress remains difficult to compare or improve. This slide broadens the discussion from individual KPIs to organizational barriers. Circular transitions often fail not because a single metric is missing, but because the whole management system is still oriented toward linear efficiency. The chapter highlights barriers such as weak top management commitment, gaps in corporate social responsibility capabilities, complex stakeholder relationships, and difficulties integrating Industry 4.0 technologies. A useful response has three parts. First, circularity indicators should measure reuse, recovery, and regeneration. Second, benchmarking should make progress visible across products, firms, and networks. Third, digital integration should improve traceability, data curation, and operational agility. Together, these tools help managers see circularity as a measurable capability, not only an aspiration. They also create evidence for investment decisions and leadership support. This section examines purchase price variance and lead time. Both metrics remain useful, but they become problematic when they dominate decisions and hide circular value, supplier quality, resilience, and sustainability. Purchase price variance, or PPV, compares actual purchasing prices with expected or standard prices. In conventional procurement, favorable PPV can signal savings. The chapter explains why this can become misleading in a circular supply chain. If buyers are rewarded mainly for avoiding unfavorable PPV, they may choose cheaper inputs, delay decisions, or use evasive purchasing tactics that raise total operating costs. More importantly, PPV does not naturally capture supplier relationships, material quality, recycled content, repairability, or environmental performance. A circular procurement team still needs cost discipline, but PPV should be treated as a baseline metric rather than the main definition of value. The broader question is whether purchasing decisions support long-term resilience and verified circular outcomes. That requires a wider view of value. Lead time is another useful but incomplete indicator. Many managers focus on reducing the average lead time, because shorter delivery appears to mean faster performance. The chapter emphasizes that the mean is not the whole story. Variability can matter even more, especially for inventory planning, responsiveness, and disruption management. A supplier with a slightly longer but stable lead time may support better operations than one with a lower average but unpredictable arrivals. In circular supply chains, this issue becomes even more important because recovered materials, take-back flows, and secondary inputs can be variable. The lesson is to measure stability as well as speed. Resilience depends on predictable flow, not simply the fastest average number. Managers should therefore track variation, mismatch costs, and reliability together. This slide summarizes the shift from a narrow linear scorecard to a balanced circular metric set. Economic indicators remain important, because organizations must control cost, efficiency, and value capture. However, they need to be complemented by environmental indicators, such as material loops, carbon impact, and avoided virgin inputs. They also need social and network indicators, including supplier engagement, governance quality, and collaboration across the value chain. The chapter does not argue that PPV or lead time should be abandoned. Instead, it argues that they must sit inside a broader system of measurement. Circular performance means combining efficiency with regeneration, resilience, and verified impact, so that managers can make decisions that are operationally and strategically sustainable. This is the foundation for the next frameworks. The following section moves from critique to practical frameworks. It explains how organizations can balance short-term efficiency with long-term circular resilience through readiness models, take-back systems, governance, and collaboration. The Circular Economy Readiness Framework is presented as a transition blueprint. Its value is that it connects circular ambition with management routines. First, it asks whether circular goals are embedded in business strategy rather than treated as isolated sustainability projects. Second, it views assets differently. Equipment, components, materials, and products are not simply costs or future waste. They are recoverable value. Third, it uses systems thinking, because circular outcomes depend on relationships across product life cycles and stakeholder groups. Finally, it aims for resilience outcomes, such as reduced exposure to disruptions and more adaptive operations. In practice, the framework helps managers translate circular economy principles into decisions about assets, investment, governance, and long-term performance. It makes readiness observable rather than abstract. Take-back systems are one of the clearest examples of circular resilience. In a linear model, products usually leave the company and become waste at the end of use. In a circular model, the firm designs channels to collect, recover, and reintegrate materials. This creates closed or open loops that can reduce dependence on uncertain virgin inputs. The slide shows a simple flow: use, collect, recover, and reintegrate. The managerial challenge is deciding how large and robust those loops should be, especially after disruptions. Optimization models can help estimate post-disruption equilibrium states and guide take-back strategy. The broader lesson is that reverse flows are not just environmental programs. They can become operational buffers and sources of strategic resilience. Recovery capacity therefore deserves active planning. The circularity paradox is an important warning. Circular initiatives often improve efficiency, for example by using fewer resources per unit, improving recycling, or reducing energy consumption. But if those improvements lower the effective cost of consumption, demand may rise. This rebound effect can cause total resource use to increase even while each unit becomes more efficient. The chapter therefore argues that circular strategy must be governed for absolute resource reduction, not only relative efficiency. Mitigation requires corporate governance, sufficiency education, and inclusive innovation. In other words, managers should ask whether circular improvements genuinely reduce total environmental pressure. Without that question, efficiency can accidentally reproduce the extractive logic that circularity is meant to replace. The target is less total impact. Therefore, governance matters. Industrial symbiosis shows how circularity can operate at network level. Instead of each company treating byproducts as waste, firms exchange those byproducts as feedstock. This can reduce disposal, lower virgin material use, and create regional resource efficiency. However, the chapter emphasizes that circular exchanges are often variable. Quantity, quality, timing, and composition of byproducts can fluctuate. That variability must be managed, not ignored. Tools such as variance flow analysis and VB-TIM help identify how firms amplify or stabilize uncertainty. The outcome is important. Short-term disruptions become a shared network problem rather than one firm's isolated risk. Industrial symbiosis therefore requires both technical matching and governance mechanisms that keep exchanges reliable over time. Trust and data make the network resilient. Circular business models require capabilities that are different from those used in purely linear competition. The slide highlights business models, open strategy, dynamic capabilities, and strategic flexibility. Value creation changes because firms must design products, services, and recovery processes that preserve material value. Value delivery changes because circular models often depend on cross-sector coordination, reverse logistics, and secondary material markets. Value capture also changes because the financial return may come from resilience, reuse, service models, or avoided resource exposure rather than immediate cost reduction. The chapter's message is that circularity is not just a sustainability add-on. It requires managers to develop new capabilities for collaboration, adaptation, and long-term strategic renewal. These capabilities shape whether circular models can scale. Repeated learning becomes essential. Measuring material circularity. It introduces material circularity metrics and explains why measurement must consider value retention, downcycling, and broader system boundaries. The material circularity indicator is useful because it gives managers a structured way to assess whether materials are reused, recycled, and kept in closed loops. It connects core flows, virgin inputs entering the system, useful product life, recovery loops, and linear waste leaving the system. The chapter's critique is that traditional 1101 can rely too heavily on mass flow calculations. A material may appear circular by weight, while losing economic or functional value through downcycling. Traditional assumptions about residual value can also be too optimistic. Newer approaches therefore add economic value and residual value indicators. These refinements help organizations understand not only whether material returns, but whether it returns in a form that still supports meaningful circular performance. Quality of recovery matters as much as quantity. This slide places material measurement in a wider historical context. Early indicators often focused on intensity of use, meaning how much material was needed per unit of output. Later, economy-wide material flow accounting expanded the view to national or regional material flows. Material footprint methods then added a consumption-based perspective, including impacts embedded across life cycle stages and global supply chains. More recent approaches, such as UNI/TS indicators and life cycle sustainability assessment, aim to integrate circularity with environmental, social, and economic evaluation. The design rule is to avoid burden shifting. A circular metric should not celebrate recycling if it hides downcycling, high impacts elsewhere, or critical material losses across multiple life cycles. Broader boundaries produce more responsible decisions. This section connects circularity measurement to daily operations. Dashboards, machine data, OME, business analytics, and eco-efficiency tools help managers translate sustainability goals into practical decisions on the shop floor. This slide explains several dashboard components. Machine utilization can be measured through power data that classifies operating states and reveals idle time patterns. This helps managers reduce hidden inefficiencies. Overall material usage effectiveness, or OME, adapts the logic of overall equipment effectiveness to material losses. It shows where material is wasted or used ineffectively during production. Business intelligence and business analytics add descriptive and predictive insight, helping supply chains respond faster. Eco-efficiency models and life cycle assessment extend operational control into resource-heavy sectors. The research gap is important. Sustainability tracking is still underdeveloped in mainstream, BI, and BA applications. Circular dashboards should therefore connect productivity, material efficiency, and environmental accountability in one operating view. Data becomes useful when it changes action. Now we focus on Scope 3 emissions. Because these emissions occur across upstream and downstream value chains, credible tracking requires robust methods, supplier engagement, digital data, and transparent assumptions. This slide compares methods for Scope 3 accounting. Input-output analysis can use firm-level or sector-level tables to redistribute responsibility across the supply chain and reduce underestimation. Life cycle assessment helps identify hidden emissions hotspots across products, suppliers, and processes. Global multi-regional input-output models add a scenario perspective by linking corporate targets to broader climate pathways and sector-specific mitigation options. Each method has strengths, but the persistent challenge is comparability. Data quality, inconsistent boundaries, and emission factor choices can create very different results. For managers, the implication is to choose methods carefully, document assumptions, and use Scope 3 results as decision support rather than treating them as perfectly precise single numbers. Transparency is central to credibility. Managers must compare results with caution. The operating model for Scope 3 combines people, data, and governance. Supplier engagement is essential because many emissions occur outside the focal firm. Companies need to communicate goals, build trust, align incentives, and support suppliers in improving data quality. A digital data layer is also needed to curate activity data, emission factors, product information, and supplier records across tiers. Carbon accountability then connects procurement, finance, operations, and sustainability teams, so responsibility is not isolated in a reporting department. Finally, results must feed a decision cycle. Target setting, sourcing, capability building, and performance review. Scope 3 becomes manageable when treated as a supplier relationship and governance system, not only an accounting exercise. The process must support continuous improvement. Ownership must be explicit. The following part explains avoided emissions from recycled materials. The key question is whether recycled inputs genuinely replace virgin materials. Credible claims require life cycle assessment, substitution logic, and auditable evidence. This slide emphasizes credible substitution. Recycled materials can reduce emissions only when they replace virgin extraction and processing in a meaningful way. Life cycle assessment helps compare the recycled pathway with the virgin baseline. The chapter gives a Japanese example showing the potential scale. Maximal post-consumer recycling was estimated to save 12.8 million tons of CO2 directly and 17.5 million tons indirectly. These numbers illustrate why avoided emissions are strategically important. At the same time, the claim depends on technical substitutability. Recycled material must perform adequately in the final product, otherwise substitution may be partial or unrealistic. Strong avoided emissions accounting therefore combines life cycle methods, market understanding, and evidence that recycled inputs truly displace virgin ones. Substitution is the core test. Avoided emissions claims need guardrails because they can be powerful but also easy to overstate. First, technical substitutability must be demonstrated. A recycled input should replace a virgin material without compromising quality, durability, or function. Second, double counting must be prevented. Multiple actors in a chain may want to claim the same avoided emission, so allocation rules and chain of custody methods are necessary. Third, analysts must consider market effects. Recycling can change demand for virgin materials and may have wider consequences for carbon stores or production systems. Fourth, policy and business models matter. Collection incentives, secondary material markets, supplier training, and supportive regulation determine whether theoretical displacement becomes real carbon reduction. Credibility depends on disciplined boundaries and documentation. Auditors need transparent evidence trails. The following examples show different circular pathways across textiles, biomaterials, vehicles, cement, and plastics, all requiring traceability, recovery capability, and stakeholder coordination. The 6 cases on this slide illustrate the operational variety of circular supply chains. Spinnover uses wood pulp, agricultural waste, and digital twins to create textile fibers with closed-loop water and energy systems. Ecolf's Upcycling the Oceans program mobilizes fishermen to recover marine plastics and convert them into usable yarn. Fool.co transforms discarded temple flowers into incense, leather, and biodegradable materials while creating social employment benefits. Mahindra CERO industrializes end-of-life vehicle recycling, recovering metals and plastics as valuable assets. Siam Cement Group uses industrial symbiosis by feeding cement kilns with alternative fuels and raw materials despite variability. Indorama Ventures scales food-grade and automotive-grade recycled PET. The shared lesson is traceability, recovery capability, and stakeholder coordination. Those capabilities replace a narrow cost-only view. The conclusion brings the chapter back to its central claim. Measuring circular supply chains means changing what counts as performance. A circular scorecard must broaden beyond cost and speed to include material circularity, resilience, and social and ecological value. It must also be supported by verifiable data systems, including LCA, Scope 3 methods, operational dashboards, and supplier data. Finally, circularity requires managing networks, not only transactions. Take-back systems, industrial symbiosis, supplier engagement, and stakeholder collaboration turn circular ambition into operational capability. The paradigm shift is from extractive accounting to regenerative, multi-dimensional sustainability metrics. When managers change the scorecard, they make circular decisions visible, auditable, and strategically defensible. That is the practical takeaway from Chapter 14. The message is deliberately practical. Thank you for your attention. Next, we continue with our last chapter of this course. Module 5, Chapter 15.